Good morning. It's Sunday, May 7th, 2023, Seattle, Washington. Here there's been some reading from Nuclear Physics by Werner Heisenberg. This great book about Markov processes and potential theory really is a lot about the superclassical or non-standard models, or things with infinity in them, about Markov processes. With regards to potential theory, and the potential theory is basically the sum of potentials, or sigma potentials or omega potentials, is the idea of all the things that together from the outside, is the outer product of all the things that add together, that in the middle result the same thing as the classical things. It's an idea of looking at things as of from the outside and helping to explain why a theory really has infinity in it, and it is this theory of some potentials that really makes all the real things. And it's not unfamiliar since the classical milieu, when you got up to electrical theory, and it no longer behaves like phenomenological models of the finite and the discrete, and that it's continuous and infinite, that it's real, and then that the super models are the super classical, extra classical, non-standard, that these kinds of things reflect the deduction, the analytical deduction that they exist, and as to why then it becomes possible to grasp them with what's called an object sense. And so I've been reading a little bit about what this is called variously, because after the senses, the five senses usually of the physical and phenomenological senses, there's this notion, there's this Platonic grasp of these numbers and their objects. And so I just call this object sense. Before it means basically the grasp of the abstractly available to reason, and so, or number sense. And such as a real thing as just as of arising from matters of abstraction. And so there's much to be said about the constructivist and the intuitionist, and about the great strength of intuition and the ability to establish for the formalist, thus that the formalist constructivist approach is what satisfies rigor, mathematical rigor. And so mathematical rigor is the strength that makes it possible to have theorems that are unambiguous and clear and provide the results of existence and uniqueness and universals where they may be. One of the great weaknesses of current modern theories is they start from the classical and they reach this kind of inductive impasse, which means that which is outside, or the space of things altogether, it attains to that, it's in the limit, so at least we have the limit, but to actually reach it, it must come back from inside as well. It must be this complementary duals. So the complementary duals go a long way to helping to frame a dialectic. So for something like Descartes' Discourse on Method, and a lot of things that Descartes had going on. Descartes is deemed a visionary, and ahead of his time, and today he's also well renowned as having kept together a lot of these theoretical concepts, not all of which today are part of the mainstream theory, but it have many close analogs, just like the ancient Greeks in the discussion last time about the theories of atomism. And it's really about the law of constant proportions, even in the infinite, that was really the idea of atomism in terms of universals. That in the modern theories, it kind of starts with points, and the identification is of those or with the empty set instead of with the universals. And so the universals lead to logical paradoxes. And so to handle the logical paradoxes, you end up having these extraordinary theories. It's like, well, we have a theory of integers. Well, what is it? It's like, well, there's infinitely many integers. It's like, well, is there an infinite integer? And the answer is kind of yes and no, because there's a model where there is and there's a model where there isn't. So it's kind of like whenever there's a model of integers, the idea is that there's no standard model of integers, because if you have one, then there's either a model of a fragment of integers or a model of an extension of the integers. And so the idea is that there's no standard model of the integers, kind of plays into these frameworks of the construction of all the numbers. You can call it set theory, you can call it number theory, But it's model theory, which is basically theory that we have a structure that represents these things. So this model theory results for the constructivist that there's a milieu for making rigorous proofs in the formal and the logical. That these are the kind of things that happen when you start thinking about infinity, that it's replete, that it's a fuller picture of these things all the time. There's these three definitions of a continuity. Standard analysis has only one, and that's all it needs to establish the standard proofs, but it ends up being insufficient for a fuller picture. And then in the physics we've been talking about, then that basically has the field continuity is called standard, and all its proofs arise from delta epsilon x very neatly. And then for something like line continuity, well, there's Jordan measure in the modern physics of the day, but to really have that be real, it needs to be a real thing. It's like not a measure. It's typed as with a class set distinction. It can't really exist. It wouldn't be formally acceptable. Would be contradictory without having otherwise these very fundaments and the foundations and fundamentals that in the elements of the primary and the centrality of such notions of continuity end up being that continuity is replete in its definitions. And so that's something that has always been part of the discourse and the debate on infinity and the a prioron since Anaximander, and of course even since before when it was much more lyrical and metaphorical, all the way back to Ananta, this idea of the ancient Indians' avatar of mathematics and this kind of thing. And Sesha, the wisdom reptile, if you will, and that the Ouroboros is what we usually think of, the snake eating his tail, that this kinds of notions of the self-similarity or the self-reference make up that the same notion that the lemniscate is like the 8 on its side, the sign for infinity, is kind of that same thing. So it's by no means new, and so what's new though about it is that there's already been now this foundations as of axiomatic set theory and descriptive set theory, which results for axiomatic geometry and descriptive geometry, and the ubiquitous success of models of geometry, that there's these things. And then various notions of the non-standard, you can start with things like Riemann and his various changes to ideas about higher order geometry. And these kinds of things that make it so that it's possible to actually start again from the bottom, as it were, and that's really where the centrality and the primariness of these elements exist, for a deconstructive then reconstructive account, that it ends up being possible to have a consistent mathematics that's also complete. And this is a theory we attain to, at least isn't already halfway gone, that somehow from these mutual ends that can be considered, there's this middle and nowhere between them, as of the inductive impasse either way, that is bridged, that is crossed. And so as we've been reading for Einstein, one thing that he makes clear in his philosophy of these things is that there's these bridges between what are the large central symmetry moments, like planets and orbits and what, about how then that makes a Riemannian tensor about them in a bit of different geometry in its own little world, its own space, and this world, as he's assigned it this space, that SR, special relativity, is local within that. It really makes for a thing that Einstein, is what we've been reading, has left it that he wouldn't later be simply disqualified for having an utterly contradictory theory in itself. And so a lot goes on with that with regards to making it possible so that science can be a mathematical science, and it's great. So where we left off with was a discussion in this chapter 14 of the fundaments of theoretical physics, and we talked about Hertz and Faraday and the electron physics, and the great things that come up after like Loschmidt and these kinds of things in reading from the atomistic theories from the Heisenberg's book. So he talks about J.J. Thomson, who pointed out that an electrically charged body in motion must, according to Maxwell's theory, possess a magnetic field, or it interacts with the magnetic field. From it, a field interaction arises. whose energy acted precisely as does an increase of kinetic energy to the body. That this energy is our milieu of exchange of these things. And so oftentimes fundamentally in physics they'll say it's all energy, everything is energy. But it is also as well that in these different milieus that the exchange only happens through very specified processes. These are these continuity laws that affect transitions on either side. This is for Emmy Noether's theorems of that every symmetry implies a conservation law. I point to this young man named Scheck, and he wrote a book in a paper that basically outlines philosophically that actually every symmetry implies a continuous transformation according to continuity laws. And I have myself this kind of usual idea, and it's so as we would talked about here, the additive identity zero and identity is about zero, and end up being continuity laws on either side of zero, and then also for the product terms in dividing one into pieces, and multiplying one by pieces smaller than one, is an opposite kind of thing that is just the other side of the same coin. That the multiplicative identities for the additive identities represent two factors of even this construction of arithmetic that's deconstructed. That otherwise people always have all the field operations together, but you can also model it and attain to it as this model of two groups that have these properties about what arises in the middle of them. So via this act of deduction, you can end up having a more fundamentally limited, simpler objects, the objects of arithmetic after their operations are closed, that results still then it just has one field where both the operations are closed, these complements or these ones implemented in terms of the other. Yet as well, then what it gets to is that similarly in the analogy to energy, and that mass and charge are underneath that, and then color and light, and then that that energy is the medium itself, gets into a lot of things making it so, and then it's possible for these numbers that are like so, and then for Einstein's space-time and Einstein's space and time at each point, where he has time is woven through everything, and then about the metrics of Riemann, which makes for a gauge theory and torsions in the highly nonlinear and singularities, and then what results, why that can be built together is about this exchange, what here is called cube wall, about the inverse square and the linear, about boundaries and continuity laws. And so this kind of reflects a whole deconstructive approach of what we have as the theory and the philosophy of the theory and Noether's theorem and these kinds of things that end up making for more replete the whole theory better. So here Einstein continues. The development during the present century is characterized by two theoretical systems essentially independent of each other, the theory of relativity and the quantum theory. So that of large bodies and the celestial, and that of subatomic particles. The two systems do not directly contradict each other, but they seem little adapted to fusion into one unified theory. We must briefly discuss the basic idea of these two systems. So it's kind of nice, at least then, that mathematics already has this idea of these complements, these complementary duals, about the exchange of them in the middle in this medium, what makes for then that something like a fall gravity is what sits in the middle, and so that results just being the usual an interpretation of Newton's zeroth laws. And this addresses a lot of different things that are part of Einstein's desiderata and requirements of future physics. So he continues. The theory of relativity arose out of efforts to improve, with reference to logical economy, the foundation of physics as it existed at the turn of the century. So fin de siècle, the year 1900. The so-called special or restricted relativity theory is based on the fact that Maxwell's equations, and thus the law of propagation of light in empty space, are converted into equations of the same form when they undergo Lorentz transformation. This is with regards to that Lorentz transformation establishes this metric about the space-time that light's included. The And light speed as a constant is a measure of, essentially, it's a fundamental physical constant. Okay. This formal property of the Maxwell equations is supplemented by a fairly secure empirical knowledge that the laws of physics are the same with respect to all inertial systems. This is a slight conceit because inertial systems are underdefined as independent systems themselves, vis-a-vis all inertial systems, that overall that they are each independent, while all together. That is the conceit. This leads to the result that the Lorentz transformation applied to space and time coordinates must govern the transition from one inertial system to any other. The content of the restricted relativity theory can accordingly be summarized in one sentence. All natural laws must be so conditioned that they are covariant with respect to Lorentz transformations. So here there's the idea that Fitzgerald was the guy who first came up with the idea of space contraction. That these days it would be reformulated a bit to make it so that there's one metric and one gauge, and how it works out that it, as a function, that it's the metric and the gauge, so that otherwise Einstein's bridges need to be everywhere, from every point in space-time to every other point in space-time. While that still needs to fit somehow in this paucity, this efficiency of the principle of least action of only a few dimensions. From this it follows that the simultaneity of two distant events is not an invariant concept, and that the dimensions of rigid bodies and the speed of clocks depend upon their state of motion. A further consequence was a modification of Newton's law of motion in cases where the speed of a given body was not small compared with the speed of light. There followed also the principle of the equivalence of mass and energy, with the laws of conservation of mass and energy becoming one and the same. And so this reflects upon and speaks to the bit of discussion just now about that it's an exchange. That conflating them is when it's like we can erase their differences via this act of extensionality and treat them as the same. Then that qualitatively and quantitatively, then we can make a balance of them and establish that the symmetry and invariance exists, that there's a zero in the middle, so you can zero it out and make a balance. At the same time, it doesn't eliminate that that's only as a matter of course. And as well as that energy is for quantities of charge and charge potential, is that's a derived quantity itself from what's otherwise these quantities that are energy. And so this is a relevant thing, that otherwise that the laws of nature, or what are the formulas that are described in these terms, still hold up this way. They just need to be factorized in the sense that they're decomposable. There's a deconstructivist account, how to make that a reconstructivist account to arrive at a constructivist account that's not incomplete. Once it was shown that simultaneity was relative and depended on the frame of reference, every possibility of retaining actions at a distance within the foundation of physics disappeared. It became hidden. It was, as of above, these product terms would have to be factorized. Since that concept presupposed the absolute character of simultaneity, it must be possible to state the location of the two interacting mass points at the same time, and even on the same basis of time. And whether if time always goes forward in all systems, and time symmetry has never been falsified, still this so that the motion in time can go slow or meet. So any two systems, whether they're exchanging or not, is basically what makes in effect whether or not they have the same time. That otherwise, though Einstein earlier made a strong defense, it just to help clarify that he's establishing that this is so under these terms, that there are these other terms that so establish that there's a time that's as of the more universal, or Einstein's declaration that he supports a clock hypothesis or a universal time. This simultaneity these days is called relativity of simultaneity because it's relative still. It's not that it's absent, it's just relative still. And then that this relativity of simultaneity usually these days is what results. SR is local. SR is local. And so what is this extra local, or anything about actions at a distance is extra local, and it reflects the global with respect to otherwise these systems that are governed by SR in their close ranges and their near fields, but their far fields have these nonlinear terms, and this is the theory of some potentials, which makes them like so. It is like so. The general theory of relativity owes its origin to the attempt to explain a fact known since Galileo's and Newton's time, but hitherto eluding all theoretical interpretation. The inertia and the weight of a body, in themselves two entirely different things, are measured by one and the same constant, the mass. From this correspondence follows that it is impossible to discover by experiment whether a given system of coordinates is accelerated or whether its motion is straight and uniform, and the observed effects are due to a gravitational field. This is the equivalence principle of the general relativity theory. It shatters the concepts of the inertial system as soon as gravitation enters in. It may be remarked here that the inertial system is a weak point of the Galilean Newtonian mechanics, for there is presupposed a mysterious property of physical space conditioning the kind of coordination systems for which the law of inertia and the Newtonian law of motion hold good. So here this reflects this notion that the space contraction has objects are together or apart, and coming together or going apart, this about this being and becoming, and this going and ongoing, and all these kinds of things that do make for that, then this system of coordinates and this kind of stuff is a vague fugue in terms of ordering, that the ordering and thus the causality and the that which precedes and that which follows, to be well defined, has that it reflects more these notions of the warp than the weave, as it were. And so when thing about symmetry breaking is that when symmetry breaking happens, then basically anything could happen. When Einstein says shatters, it means that we basically have something that is entirely rigid, and when it breaks everywhere at once. There's no flex. So this idea of symmetry flex is to reflect what goes on also with quasi invariance, and it's a thing. And like from the studies of Oproka and Bergson, the quasi invariance for measure theory is the mathematical thing that helps detail what these things are. Why symmetry breaking is first symmetry flex if it's actually a matter of exchange. That otherwise there are all sorts of almost invariance or those things that are the rigid that help explain why then Einstein is having bridges everywhere between his absolute flat space-time and each of the spaces on the geodesy in his general relativity, and each of the tensors metrics spaces that are so attached, and then that the exchange and the translation between these are the transformation, as of about entropy, I suppose, if that word comes from transformation, really just means motion. And so that motion is geometry is motion, is basically a self-contained point that the form and proportion is as well changing. The constant is change. That being just a very facile sort of mental panacea for otherwise that everything gets shattered or it's broken, the theory helps to explain how it has to come back together. There's a natural tendency and propensity for the objects, of course, to proceed as they will, because it's natural. It's a natural law. And so the gravitation and the kinetic is about these inertial systems and about the terrestrial frame, which is the entire world, and us as ants on it, and and all their kinetics and kinematics, still that on Einstein's train, Einstein's teacup, he can stir it, and when he brings it to his face, it is a nice sip. These difficulties can be avoided by the following postulate. Natural laws are to be formulated in such a way that their form is identical for coordinate systems of any kind of states of motion. And this is essentially having that these natural laws as of the motion is always a continuous exchange. It is this milieu of these things, and there's a big difference between the linear motion and the angular motion. And there's that kinematics of rigid bodies make for combined linear and angular motion, and so it becomes kind of a muddle. But he's helping explain that besides that there's tensorial products that carry transformations as about the linear, the nonlinear, the highly nonlinear, and the singular that results straight lines through all that. That also there's this super covariant notion that is this anti-covariant notion at the same time. It's sort of an extra coordinated notion that is a higher level mental construct than the usual writing of things in terms that result they have regular geometric forms, that they still do. And so this is the kind of thing that gets to what it means to have this these complementary duals, so that there's the bridge everywhere for Einstein's space everywhere, for special relativity everywhere in terms of otherwise general relativity, and that also linear motions in classical is linear in motions as well as in its usual derivations and solutions, and according to the order of usual higher order terms, they're products, that it results one thing. So this is how he's saying the difficulties can be avoided, because before they are kind of void because they're not distinguished in this manner, but making it so that they can be distinguished in this manner raises it out from that as to the primordial. On the other hand, we deduce from the restricted theory the existence of a Riemannian metric within the time-space continuum, and in fact you assume they exist anywhere there's an arbitrarily larger body, because that affects basically a larger frame, which according to the equivalence principle describes both the gravitational field and the metric properties of space. And so this affects, when we have this space contraction, that it's at least two things. It's rotational space contraction and linear space contraction. The linear space contraction, the object carries the space along with it. The rotational space contraction, the object sits in its space. Both of which, though, have the energy in it that affects what makes for momentum and inertia. And these quantities that also then makes for that in his rest exchange momentum theory that's like the Loch Ness Monster. And what does it look like? It's like, well, nobody's ever seen it. But what does it mean? It's like, well, it's like a snake in the water, and so it humps its way across the lake, and then you can see its loops of its body above the water, but then there's also that underneath. Together, it makes its way across the lake. And so this is the kind of notion that Einstein's on a train, he's sipping his tea, he sees the Loch Ness Monster, and he has a theory that it's not just what he sees. And so this is the kind of thing that here he establishes that there must be some bridge, and according to the Riemannian metric, that the snake is attached to the earth via the part under the water. Now that's just kind of a non-satsa, a Gedanke, a bit of the metaphorical means that then he says, and my tea is still spinning. I'm still stirring my tea. Describes both the gravitational field and the metric properties of space. Assuming that the field equations of gravitation are of the second differential order, I kind of see this as meaning inverse square. The field law is clearly determined. In fact, it's kind of closed, and the idea is that in the theory of some potentials, it's like that's just an approximation, which is fine, and it's great, and it's predictive, and it's of value. It's closed, it's incomplete. Einstein continues, aside from this result, the theory frees field physics from the disability it suffered from in common with the Newtonian mechanics of ascribing to space those independent physical properties which heretofore had been concealed by the use of an inertial system. Here it's that it is an inertial system, this space. So, but it cannot be claimed that those parts of the general relativity theory which can today be regarded as final have furnished physics with a complete and satisfactory foundation. See, Einstein is a generous and grandiose hedge, and he's self-aware, at least to the point that he makes it clear that what he's got is good, and here, as he put it, final. This is Einstein's final version of relativity, essentially, and it's great. That he is aware of its limitations, so that he's not a dupe. In the first place, the total field appears in it to be composed of two logically unconnected parts, the gravitational and the electromagnetic. And here we frame this in terms of the kinetic and mass and the electromagnetic and charge. Okay. And their flows of massy bodies as essentially rigid and up to the kinematic as rotational, and flows of current as the potential, and as of about the induction of current. And in this second place, this theory, like the earlier field theories, has not up till now supplied an explanation of the atomistic structure of matter. This failure has probably some connection with the fact that so far it has contributed nothing to the understanding of quantum phenomena. To take in these phenomena, physicists have been driven to the adoption of entirely new methods, the basic characteristics of which we shall now discuss. And so here, as we've been talking about atomism and the Democritan and the theory of constant proportions and NIST codata and fundamental physical constants and how they have been seen to decrease over time with increasing energy of experiment. Then there's the notions of the continuum mechanics and the atomism of the Democritan, and underneath that the Planck length. And then as about angstroms and the optical properties of optical visible light and its color. And then also with regards to superstrings as arbitrarily smaller than atoms, as atoms are smaller than us, all about being a continuum mechanics. And then there's these dynamics of mathematics, that mathematics owes physics how continuums work, like in this quasi-invariant of Bergson and Oproka that was mentioned, would make it so that we can have Borel and combinatorics get back together because there are more laws of large numbers, because any standard model of an integers with an infinity or not that exists would also have one that is non-standard model or a fragment, that there's an extra standard model of numbers, the basic characteristics of which we shall now discuss. In the year 1900, in the course of a purely theoretic investigation, Max Planck made a very remarkable discovery. The law of radiation of bodies as a function of temperature could not be derived solely from the laws of Maxwellian electrodynamics. And here we often point to Rayleigh Jeans and Rayleigh. Rayleigh was pretty great. And then there's Kelvin, and then there's also Clausius, and all these matters that result, we have discretization. And that Millikan found that an electron has a given mass equivalency. This is discretization. For our atomic theory, this is the floor. This is the limits of the regime, under which is the transatomic regime, trans-Planckian regime. Continuum mechanics. To arrive at results consistent with relevant experiments, radiation of a given frequency had to be treated as though it consisted of energy atoms of the individual energy HV, H dot V, where H is Planck's universal constant. It's a ratio reflecting form of constant proportions of mass and length in the very, very small. During the years following, it was shown that light was everywhere produced and absorbed in such energy quanta. This is a remarkable fact, and again, it has to do with Rayleigh genes and the optoelectronic and the notion that there's electron theory, and that the detectors on such a range basically reflected that those definitions are stacked on top of each other. It's called the ultraviolet catastrophe. And it has to do with discretization of a continuum so that we can have predictive value in finite terms, and it's great. During the years following, it was shown that light was everywhere produced and absorbed in such energy quanta. In particular, Niels Bohr was able largely to understand the structure of the atom on the assumption that atoms can have only discrete energy values and that the discontinuous transitions between them are connected with the emission or absorption of such an energy quantum. This is usually with regards to the orbital models of the electrons, and that these notions of the discrete are based upon an entire related apparatus in the configuration of experiment and the energy of experiment. This threw some light on the fact that in their gaseous state, elements in their compounds radiate and absorb only light of certain sharply defined frequencies. But light itself is decoherent, it's called, but it just means white in the usual sense, or that is just a term reflecting that it has all the colors in it. Usual radiated light as of the thermal and these kinds of things. Not that I'm being contrarian, but it's this sort of context being inserted is relevant because what it reflects is otherwise this entire worldview that things are continuous. And it's necessary to so explain why the predictive power of science is not because the world is discrete and digital, but because these methods so arise that make it possible to get a grip on the infinitesimally small or the infinitely large at all. All this was quite inexplicable within the frame of the hitherto existing theories. It was clear that at least in the field of atomistic phenomena, the character of everything that happens is determined by discrete states and by apparently discontinuous transitions between them, Planck's constant h playing a decisive role. Now these days you can find many systems where Planck's constant basically goes to zero. It's a running constant. The next step was taken by de Broglie. He asked himself how the discrete states could be understood by the aid of the current concepts and hit on a parallel with stationary waves. As for resistance in the case of the proper frequencies of organ pipes and strings in acoustics, true, wave actions of the kind here required were unknown, but they could be constructed and their mathematical laws formulated employing Planck's constant h. De Broglie conceived an electron revolving about the atomic nucleus as being connected with such a hypothetical wave train, and made intelligible to some extent the discrete character of Bohr's permitted paths by the stationary character of the corresponding waves. This is also about the spectral analysis and the root mean square and finding a discrete value out of what's otherwise a continuous medium. And in summing things, it's the mensuration. Now in mechanics, the motion of material points is determined by the forces or fields of force acting upon them and the principle of least action that they so go in their spaces, which here they are in, and as they go are with them. Hence it was to be expected that those fields of force would also influence de Broglie's wave fields in an analogous way. Erwin Schrödinger showed how this influence was to be taken into account, reinterpreting by an ingenious method certain formulations of classical mechanics. So this is the Schrödinger picture as of after the Heisenberg picture, and there's been a lot of talk here about it in reading about the path integral. He even succeeded in expanding the wave mechanical theory to a point where, without the introduction of any additional hypotheses, it became applicable to any mechanical system consisting of an arbitrary number of mass points, that is to say, possessing an arbitrary number of degrees of freedom. And here the degrees of freedom is a big deal, and this is where the functional freedom these days is the modern catastrophe, and is the functional freedom catastrophe, and it's that, well, there's 120 orders of magnitude higher, wrong, that relativity is shown good one way, 30 degrees order of magnitude, and quantum mechanics is shown good the other way, 30 degrees order of magnitude. But according to these fundamental freedom and degrees of freedom, that somehow ends up being wrong. So somehow we need to figure out how that all gets added back up in the middle, as not with otherwise these indeterminate things. Putting down any multiple worlds hypothesis, because we still don't have a single one yet. We've got a universe. So solving this up for then these bodies and the aggregates and the systems and how they worked up, that as well, it affects what's the propagation of these waves, the motion of these points. The same thing. It's particle wave duality. This was possible because a mechanical system consisting of n mass points is mathematically equivalent to a considerable degree to one single mass point moving in a space of 3n dimensions. On the basis of this theory, there was obtained a surprisingly good representation of an immense variety of facts, which otherwise appeared entirely incomprehensible. But on one point, curiously enough, there was failure. It proved impossible to associate with these Schrödinger waves definite motions of the mass points. That, after all, had been the original purpose of the whole construction. The difficulty appeared insurmountable until it was overcome by Born in a way as simple as it was unexpected. The de Broglie-Schrödinger wave fields were not to be interpreted as a mathematical description of how an event actually takes place in time and space, though of course they have reference to such an event. Rather, they are a mathematical description of what we can actually know about the system. They serve only to make statistical statements and predictions of the results of all measurements which we can carry out upon the system. This is that the super wave, or this pilot wave that so guides it, is having arbitrarily large spin, just like it's an arbitrarily small quantity. It's kind of a reflection of Heisenberg's uncertainty into the Schrödinger picture, and for a reflection of the Schrödinger picture into the Heisenberg picture. Uncertainty one way, wave collapse the other way. That it's a thing that makes it so that while the quantum mechanical statistical interpretation of the statistical ensemble is great, and it's scientific, and it's a reflection on the means and the tools, that's also about how great it is. And Born's book about the restless universe is a pretty good book. Let me illustrate these general features of quantum mechanics by means of a simple example. We shall consider a mass point kept inside a restricted region G by forces of finite strength. If the kinetic energy of the mass point is below a certain limit, then the mass point, according to classical mechanics, could never leave the region G. But according to quantum mechanics, the mass point, after a period not immediately predictable, is able to leave the region G in an unpredictable direction and escape into surrounding space. This case, according to Gamow, is a simplified model of radioactive disintegration. Hearing all this talk about the fields of mass and charge, what's left out is this electroweak light radiation in color, or heavy color, these nuclear forces of the weak and electroweak, the radioactive. Where radioactive in the electromagnetic means usually referring to radio frequency waves, whereas radioactive in the thermonuclear is about the lifetime of the proton, and otherwise the real slow force. If light is the real fast part, then nuclear color is the real slow part, and similarly is how mass and charge are equivalent according to the equivalence principle. That this light and color are similar. here I've been overusing the word color, and it's just kind of reflect this for the strong nuclear force, the color force that holds atoms together, the gluon and quarks, quark gluon plasmas and such, and about the various particles in the particle zoo. And I need to learn more about this pi mesons and the mesonic, according to Feynman, and that's this Feynman is along the lines of, I am an electron physicist, and so the pi meson is my playground. You know, it's thermonuclear, and there's this kind of thing, and then Gamow is pretty interesting. I'll need to study him some more, compared to like Solomon Weinberg and who is that people? The lots of the great physicists of the 60s and 70s and 80s and the 50s. The quantum theoretical treatment of this case is as follows. At the time T0, we have a Schrodinger wave system entirely inside G, but from the time T0 onwards, the waves leave the interior of G in all directions in such a way that the amplitude of the outgoing wave is small compared to the initial amplitude of the wave system inside G. Further, these outside waves spread, the more the amplitude of the waves inside G diminishes, and corresponding to the intensity of the later waves issuing from G. Only after infinite time has passed is the wave supply inside G exhausted, the outside wave has spread over an ever-increasing space. But what has this wave process to do with the first object of our interest, the particle originally enclosed in G? To answer this question, we must imagine some arrangement which will permit us to carry out measurements on the particle. As described before, it's sampling, observer, and measurement effects have that it's interfering with an infinitely or arbitrarily high frequency spin of the wave, and of the pilot wave or ghost wave, and so it's a thing. To answer this question, we must imagine some arrangement which will permit us to carry out measurements on the particle. For instance, let us imagine somewhere in their surrounding space a screen so made that the particle sticks to it on coming into contact with it. Then from the intensity of the waves hitting the screen at some point, we draw conclusions as to the probability of the particle hitting the screen there at that time. As soon as the particle has hit any particular point of the screen, the whole wave field loses all its physical meaning. Its only purpose was to make probability predictions as to the time and place of the particle hitting the screen, and that's the exchange has occurred. Another one might soon happen, but that's the matter of exchange, and this transformation of the energy is the event, not the energy's location, the actual existence of its state. Its only purpose was to make probability predictions as to the place and time of the particle hitting the screen, or for instance, its momentum at the time when it hits the screen. This is, for example, referring back to the Heisenberg's uncertainty that you can't know both the position and momentum at once because it's a particle and it's a wave. But when it does hit, according to how good the clock precision is, it's known. All other cases are analogous. The aim of the theory is to determine the probability of the results of measurement upon a system at a given time. These are the probability amplitude transitions, the amplitudes of the probability of transitions from our path integral. On the and with or without here a real wave collapse of a Bohm-de Broglie wave of the quantum mechanics in the propagation of particles like electron holes as a reciprocation of electrons and photons, which are the usual milieu of these experiments, because there's also the high energy experiments involving the kinetic particles like a proton accelerator or a neutron bombardment. I don't know much about. On the other hand, it makes no attempt to give a mathematical representation of what is actually present or goes on in space and time. It has to somehow fit in all the other representations that there are, though. So somehow it's on Einstein's bridge. On this point, the quantum theory of today differs fundamentally from all previous theories of physics, mechanistic as well as field theories. Instead of a model description of actual space-time events, it gives the probability distributions for possible measurements as functions of time. Still, the events themselves, as are observed, that's the observables of the statistical ensemble, samples, are events. It must be admitted that the new theoretical conception owes its origin not to any flight of fancy, but to the compelling force of the facts of experience. All attempts to represent the particle and wave features displayed in the phenomena of light and matter by direct course to a space-time model have so far ended in failure. Though this is one, And Heisenberg has convincingly shown from an empirical point of view any decision as to a rigorously deterministic structure of nature is definitely ruled out because of the atomistic structure of our experimental apparatus. And from the grainy structure, our experimental apparatus is not atomic. It's built up and as of being built down from something that was fundamentally digital or discrete. Then there's the ideas of something like nuclear magnetic resonance is really a thing, and yeah, it works also, and it doesn't have this dependency. Or that the Heisenberg's uncertainty is like Gödel's incompleteness, and so you can still have a theory of complete and consistent arithmetic, but it's not necessarily the ordinary one. Still, though, this rigorous fundamental constructivist approach is our quantum mechanics of the 20th century. Thus, it is probably out of the question that any future knowledge can compel physics again to relinquish our present statistical theoretical foundation in favor of a deterministic one, which would deal directly with physical reality. It would just still have a statistical interpretation, but it somehow has a real interpretation. It's not, and mathematics owes this. And so if mathematics can equip the models of mathematics with it appropriately, then it would automatically kind of fill in physics. Logically, the problem seems to offer two possibilities, between which we are in principle given a choice. In the end, the choice will be made according to which kind of description yields a formulation of the simplest foundation, logically speaking. At the present, we are quite without any deterministic theory, directly describing the events themselves and in consonance with the facts. But there are intuitions, there are instincts. And in this superclassical, there's abstractly whatever is, and this kind of thing. Einstein does make it clear, though, that it's not necessarily consonant with like our acoustic models that we can do in a wave tank, or our acoustic models that we can do in terms of strings and tones and overtones and fundamental frequencies and these kinds of things. And that as well, it involves having this high level extra classical model of mathematics with infinities and infinitesimals as real, and in these notions of the continuous as various, and how the exchanges happen among them and between them as effects. It's a very real thing. For the time being, we have to admit that we do not possess any general theoretical basis for physics, which can be regarded as its logical foundation. Einstein is saying saying that we do have a physics, and it's good for what it is, and it's got its limits, and you should know them if you're going to consider yourself a scientist and properly establish experiments and do so. But that this theory arising from nothing, or a whole theory of everything, is involving stuff that is not yet available to the general sensory apparatus. That goes back to the beginning of this kind of talk, this is the idea of the object sense that infinity is real, and is special, and essential, and as well various. So that's what mathematics owes physics, is infinity. Because infinity is everywhere in physics, and the great implementation of physics was that of the discretization in the quantum mechanics, because it does give us a view into the behavior of these particles and how they thus emerge as a deconstructivist account. It's just not complete yet, and there's more to follow. see. But otherwise, it sounds rather morose. He's like, we have to admit that we do not possess any general theoretical basis for physics, which can be regarded as its logical foundation. Still, though, I mean, that would be asking a lot, a theory of everything. The field theory so far has failed in the molecular sphere. It is agreed on all hands that the only principle which could serve as the basis of quantum theory would be one that constituted a translation of the field theory into the scheme of quantum statistics. So this is a good thing. This is that it's a continuum mechanics, and would all fulfill Einstein's desiderata and requirements of any future physics. Whether this will actually come about in a satisfactory manner, nobody can venture to say, because the future is not yet written. But it might happen. Some physicists, among them myself, cannot believe that we must abandon, actually and forever, the idea of direct representation of physical reality in space and time, or that we must accept a view that events in nature are analogous to a game of chance. It is open to every man to choose the direction of his striving, and also every man may draw comfort from Lessing's fine saying that the search for truth is more precious than its possession. Well, that's the end of this chapter. And the next one is the common language of science. So as I mark the book and close it, and it was signed by the person who had it back in 1980 when they got this book, or when it was printed and reprinted, that today we can thank Einstein because he's helped establish some further what is better than a usual uncritical defense of the theory. Because in his philosophical treatise here, he's provided his model physicists, the model philosophers, model theoretical physicists, intuition and instinct, with the grounds to question himself and the theory, which is a lot better than being wrong. Well, I hope you have a great day, and that it so follows. And that mathematics finally figures out what it owes physics for continuum mechanics to arrive at via some replete definitions of continuity, the mechanics of the continuum mechanics, which help make Einstein's theory and quantum mechanics a great thing. So long.